Okay, madam?
Okay, sir.
Okay, sir.
Okay. More noise. After 11. Hello?
Sir.
మీ వైపు నుంచి ఎక్కువ నాయిస్ వస్తుందండి.
డిస్టర్బెన్స్ వస్తుంది సార్. కొంచెం డిస్టర్బెన్స్ వస్తుంది సార్.
ఈ వైపు నుంచే మీరు మీ మైక్స్ క్లోజ్ చేయండి. మ్యూట్లోకి వెళ్ళిపోండి. ఓకే. సో cascode states. So as we discussed, this is the cascode states. Of course, one is the CS, where one more is the CZ. Okay, they are connected like this. This is called the cascoding of operation. So the main intention of this thing is this type of connection is what? To increase the gain as well as the output. Yeah. So already we discussed about this, how they are interacting. So if you take the bottom one is the CS, so which generally take the input signal as the voltage, and it can be flow the current in the drain, and the same drain current is applied to the as the input for the M2 transistor, and finally the output is voltage. Yeah, this is also called as telescopic configuration. So I think these two also we discussed. Whenever the two transistors gate potentials, suppose keep one is constant and another is varies, what happened in the output? This configuration, for especially for this configuration, M1 gate is changing and M2 is fixed at some voltage. So at this moment of time, so for the same changes at the input of M1, they will be replicated in the output. But in this next case, this is my next case. I think now M1 gate is fixed and M2 gate is applying a variable voltage. So for any changes in the gate potential of the M2, I think you could not find any variations in the output. That is the only difference. So here in this configuration, your M1 is acting as a constant current source, because M1 is the transistor for which whose gate is fixed to some amount of voltage, so that if the voltage VB is enough to what is it one M1 in the saturation, so then definitely the fixed amount of current is flowing in the circuit. So here the important parameter is the finding of this mix. The voltage, of course, what is the voltage? Because there are two transistors connected in the cascoding mode, but we know each individual transistor to keep in the saturation, the potential of its gate drain must be much more greater than the overdrive potential of the respective transistor. So based on that, so I'm going to calculate the Vx value. Yes, Vx value. Okay. So for the first transistor to be in the saturation, Vx should be greater than or equal to VGS1 minus VTH1. Similar.
సార్ వాయిస్ వినిపించ హలో
మేడం రావట్లేదు వాయిస్.
ఓకే మేడం.
Okay, what happened? If V in and V out. So suppose input voltage of the cascoding stage is less than the VH1. What happened? Definitely M1 is in off condition. M2, because of fixed bias voltage applied, it is in the saturation. But there is no path from VDD to the ground, so that no drop across any resistor. So your output voltage is exactly what happened? Your VDD voltage.
Screen not share, sir. Screen. Screen sharing sir. Screen.
అనిపించట్లేదా?
Screen కనిపించట్లేదు సార్.
స్క్రీన్ కనిపించట్లేదు సార్. స్క్రీన్ షేరింగ్ చేయలేదు సార్.
Is it okay now?
నో సార్. షేర్ అవ్వలేదు.
ఇంకా రాలేదు. సార్ డిస్కనెక్ట్ అయిపోయారు. మేడం ఒకసారి ఎస్ సార్ విజిబుల్ సార్. స్క్రీన్ విజిబుల్.
See, this is the cascode stage.
Yes, sir.
Output voltage characteristics. So what I'm trying to tell you here, this is the Vx potential. This is the V output potential. Okay. So whenever your input voltage is 0, as I told you, two transistors we have like this connection. Like this. So this is off M1 because whose gate potential is insufficient to switch on it. So then here you are connecting the output voltage. So our output is nothing but total VDD. So this is one. And similarly, what is the Vx? Because it's already off. Your Vx is nothing but this VB minus threshold voltage of this device, VTH2. VB minus VTH2. Yes, it starts from there. So whenever your supply for the M1 gate, which crosses the VTH1, then M1 enter into the saturation. So whenever it enters into saturation, definitely what happened? The current will flow in the circuit. Therefore, obviously, your voltages, output voltage and Vx can be decreased from the VDD and VB minus VTH2. If more input voltage is very high compared to your VTH1, then they are entering both the transistors entering in the triode. Both the transistors are entering in the triode region. Therefore, what happened? You will get a very small amount of V out and Vx. Because the condition, whatever you, the condition, because this is the VD. What VD means? VDD means what? Output voltage. This output voltage potential is decreasing. Sometime it may come below its overdrive potential. Then what happened? It flipped from the saturation to the triode region. Once the M2 did the same thing, because of the change, M2 also affected. But I don't know who will first enter the saturation. Sorry, flip from the saturation to the triode region. I can't say exactly, but the situation will happen. I don't know who is the first. So that's why your output is not enough. Yeah. So now, if you take the small signal characteristics, what is the equivalent circuit? Because you have a two transistors that are connected in the one upon another. So this is the CZ, this is the CS. Since they are connected like this, I will also draw the same manner. You know, individual transistor, small signal, equivalent circuit. Okay, there is nothing is new there. Everything is, you know. But the thing is, the way they connected in the circuit, I kept the equivalent circuit also like that. One upon another. Okay. Yeah, output resistance for the same configuration. How to find the output resistance? Yeah, output resistance is nothing but so output voltage by output current. Okay, anyhow, so for calculation of the output resistance, everywhere I told you in the especially in the analog IC design or analog VLSI design, you must be keep in your mind. Whenever you want to go for output resistance, definitely you should follow either Norton or Thevenin's theorems. Okay, that is you should fix for this because the circuit may have the equivalent circuit may have dependent sources. So straight away calculation of the output impedance is difficult. So they definitely should follow some rules. So not some rules, some procedure. So that keep all the independent sources grounded. Here is grounded myself. Why VB is the independent source and Vin is the independent voltage source. So make them ground. And the rest of the sources, which one is the GM2 into V2, GM V2. So and these things we can't do anything because they are dependent. We don't know the impedance across it, so that we cannot replace them with their internal impedances. That is the main issue. So that definitely while you are going to calculate the output resistance of this type of circuits, definitely should be very careful how to find it. Okay. Yeah, of course. Triple cascade. Triple cascode. Cascode earlier, two transistors they are connected in the one upon another. That we said called cascode. What is a triple cascode? Three transistors should be connected in such a manner. For what purpose? To improve the output resistance. The reason to increase the number of transistors in the cascode is to improve the output impedance. Clear? So generally output impedance of the transistor is mass transistor is less. Because output junction, which is in between the drain and source, is forward bias. Clear? So that is the reason. That's why you may get the very low output voltage at the output. So whenever you got the low output voltage, definitely your gain will be affected. So that is the reason. That's why I want to enhance the output impedance in whatever the way I have possibility. So this is my way of possibility that I can increase the number of transistors in the cascoding. Then I can increase its output impedance. So this is the triple cascade. You can keep 4 transistors also. Yeah. So generally here the output is increased by this much factor. So because this is the M1, this input is applying for the M1 signal. How much impedance or how much impedance or resistance will be improved whenever each transistor is connected in the cascade? The increasing output impedance by increasing the device length or cascade. So we have two choices to increase the output impedance. One I told you, keep more number of transistors in the cascading stage. And another one is, if not possible, go for the changing of the length. If length is increases, definitely your output impedance is increase. Clear? So length increases means what? See here. So this is, if you take the first picture, okay, only one transistor M1 whose length is L and W is with this fixed W. If I change, so this as like the same transistor, would I have increased the length 4 times, still the same current flows, no change, but impedance little bit increases. Or one more configuration, this is the cascode, this is the cascode. This is one of the possibility and this is one more possibility. This possibility we are seeing already. This is the possibility. This is what? Cascode. This is what? Increasing the length of the transistor. The two best possibilities we have. For what purpose? To increase the gain. Sorry. Output impedance or output resistance. Either you can do this or this. But definitely each individual will have more complications. But ideally I can speak that we have two options. You can go with any one of the options. Either this or this. Yeah, well, next one is yes, NMOS cascode amplifier with PMOS cascode. NMOS cascode amplifier is the load. In earlier case, what happened? Both the transistors in the cascode are NMOS. Now, what I am trying to explain you, load should be changed to PMOS. If the amplifier is NMOS, cascode amplifier is NMOS, all the transistors in this NMOS, then load should be PMOS. Okay, this is my solution. This is the cascading, no doubt at all. But above, there must be a, what is that? Yes, RD resistance is there. It's the RD. RD is there. But at the beginning, we already discussed about that. There is a complication of RD, taking up the RD, consideration of the RD. Because of fabrication difficulties, space difficulties. A lot of things are there. And moreover, there is an issue of accuracy of the particular resistor value. So, to nullify all the issues which we want to, when we consider, so RD, okay, so definitely in place of RD, we can keep a transistor, which must be operating the saturation. Okay, so that is the thing. So here, that's why in place of RD, I kept again transistors, but this time I'm keeping the PMOS transistors. Okay, so for both the transistors, for individual transistors to keep in the saturation, fixed amount of the gate potential is applied. Clear? So whenever this transistor is acting as one current source, this transistor is acting as one current source. That's my point. So this is the cascode amplifier, no doubt. For this load is now cascoding of PMOS transistors. Last, what are we doing both? Okay, anyhow, I think to calculate this resistance, we are using the AMR. Is nothing but what? Not transistor. So in the last class, I told you. Now, poor man's cascode. What do you mean by poor man's cascode? Suppose a layman, a common man. So by seeing your cascode connection, he may connected two transistors. He may thought that I can take the two transistors if they connected, so their gates together, then it becomes the cascode. Am I correct? So that I'm going to. So here is my. This is the poor man's cascode connection. We are not keeping like this, no? We are keeping what? This must be a some fixed voltage. This is the input is applied to here. But as I told you, a common man, he may think like that. It is nothing wrong if I connect like this. Because according to his point of view, he is applying biasing is for both the transistors. Okay. So see, read the statement. A minimalist cascode current source omits the bias voltage necessary for the cascode device. Shown in the figure, this poor man's cascode places M2 in the triode because this goes to the triode resistor. Because what happened? This is the condition. Your VGS1 is greater than VTH1. So this is the VB. Okay. So this is the VTH of this device. If you compare, this is greater. Okay. Whenever this is greater, definitely what happened? So your VDS2, this is the drain potential. VDS2 means the same voltage. Understand or not? VDS2 means here the potential. What is this potential? Same potential. The difference between these two potentials. VGS1 minus VTH1. Okay. So VDS2 is equal to VGS2 minus what? VGS1. Okay. Otherwise, you can say this is VGS2. Okay. Minus VGS1 is less than VGS2 minus VTH2. This is the, of course, what is these two? These two are nothing but if you take the difference like this, it means what? So individual transistor overdrive potentials. Suppose if they are insufficient to keep both the transistors in saturation, then definitely what happened? Your cascode, what is the term? Aim will not be satisfied. So that's why he said it's a poor man means if you think like that, if you join the gates of both the transistors and apply a fixed voltage to it, then it will not satisfy the what condition of the cascode. Okay. In modern CMOS technologies, however, the transistors with different threshold voltages are available. Yes, exactly. If you take a process, particular process means 180 nanometer process or 90 nanometer process, or if you go for the some particular what is the one fabrication company, okay, like TSMC, okay, and SCL, Tower Jars. If you take anything, if you check their library, we can have a different transistors with different threshold. Don't we think? So, for example, there is in the library of SCL 180 nanometer technology, we have a one transistor, NMOS transistor with this amount of the threshold voltage and PMOS transistor with this threshold voltage. Earlier, for a technology, the threshold voltage is fixed, but now they're keeping more transistors with different threshold voltages. Okay, what is the advantage? So, whenever this type of conduction if you take, then they will take an advantage. So, allowing M2 to operate in the saturation if M1 has a lower threshold voltage than the M2. Yes. Earlier, what is it? M1, M2 are both are same WL ratios, same threshold voltages, because both are NMOS transistors. If not, you can think in different way. But from the picture, I can say that both are same NMOS transistors. So definitely we have a NMOS transistor means 0.5 volts or 0.3 volts threshold voltage. Okay, so anyhow, whenever you keep both different M1, M2 at different threshold voltages, then what happened? M1 has a lower threshold voltage than the M2. For what purpose? To keep M1 in the saturation. Then the above condition is wrong. Maybe M1, that means M2 or M1 threshold, M1 drain voltage may be greater than the its VGS2, VGS1 minus this one. If VTH2 minus VTH1 is 150 millivolts, yes, VTH2 minus VTH1, the difference between this device is 150. Generally, the difference should be 0. Am I correct? If both are same, what is the difference? According to this condition. Rendu same అయితే difference ఎంత వస్తుందండి? 0 వస్తుంది. But he is saying some difference. Means definitely VTH2 is more than the VTH1. Am I correct? From the formula. So and if VGS1 minus VTH1, this here, this potential. Sorry, this potential. Or overdrive potential of this color is less than the 100 millivolts, then M2 is the saturation and circuit act as a true cascade. M2 is saturation because this potential VGS1 minus this potential is okay. So less than 100 millivolts, clear? So that this will be in the saturation. Earlier, when we start the concept of poor man's cascode, I told you that this is not good. But this is good only when we have a two transistor with different threshold voltages. Yes. Shielding property. So we have already change in drain current in response to the change in applied voltage to drain, that the high output impedance arises from the fact that if the output node voltage is changed by V. We already discussed about this. Basic cascode circuit, if you take, we have two gates. One gate is suppose M2 gate is at VB, M1 gate is fed with the Vin. There one question we raise is that what happened at the output voltage if changes takes place at each individual gates. From that concept I am telling you. So recall from the figure, change in drain current. Change in drain current means change in output voltage. In response to change in applied voltage, the drain that the high output impedance arises from the factors by a small voltage of V. The resulting change at the source of the cascode device is much less. In essence, the cascode transistor shields the input device from the voltage variations of the output. Okay. The shielding property of the cascode proves useful in many circuits. So this is the sentence you need to remember. The cascode transistor shields the input device from the voltage variations of the output. So in the basic cascode, what is the input device? CS amplifier. What is the cascode device? CZ amplifier. CZ stage. So CZ will protect the CS. CZ will protect the CS or shields the CS for the variations of the output voltage from the corresponding voltages in the input. So it will protect, it will shield. That's why it's called the shielding property. Here is the, so this is the M1, this is the M2. Vx is applied here, for example, or fixed voltage is applied here. So in this case, output sync of cascode stage. See, the shielding property of cascode so diminishes if the cascode device enters the triode region. This is the protection or shielding is true until they are in the saturation. Once they are entering into the triode region, as I told you, as I shown the characteristic curve, output voltage versus input voltage. So I think this, whatever the purpose, may not be stuck. The next concept is folded cascode. Yeah, we know the cascode, but what is the folded cascode? Folded. If you connect the two devices, I'm not changing anything. If you connect the two devices, so like this is the input, and once again you are applying. So whose output is connected to the again for the what happened? CZ configuration. But here is earlier M1 transistor is the NMOS transistor. M2 also NMOS transistor. But here I changed. Okay, M1 or replaced M1 with the NMOS with the PMOS. This is PMOS. This is NMOS. If you connect like this is called the folded cascode. Cascode, no doubt at all. Folding. You are keeping connection like this. If you connect the PMOS, NMOS here, you cannot connect like this. Because of PMOS, you are considering here in place of M1. And so CZ is again NMOS only. So you can connect like this. The source of PMOS is always connected to the VDD. Source of NMOS is always connected to the ground. So this is called the folded version. The simple folded cascode is this one. First picture. Okay. So the idea of cascode structure is to convert the input voltage to the current and apply the result to the common gate. Yeah, of course. Input device role is what? Input device is what? CS. Take the voltage and output is converted as the current, and the current is fed to the or applied as the input for the CC amplifier. Ultimately or finally, its output is voltage. So here, what I'm saying to you, the same concept. Here, the input device and cascode device need not be the same line. Earlier, we kept that. We keep like that. I mean, input device is CS NMOS, and cascode device is CZ again NMOS. But it is not mandatory that to keep like that. Maybe different devices you can use. Yes. So if the first figure, in the first figure, okay, PMOS NMOS combination perform the same function. This is the first picture. So in order to bias M1 and M2, a current source must be added in the second stage. Yeah. How can you make the how can you bias these two transistors? So with a fixed current source. For this, in the second picture, what biasing is applied? In the first picture, no biasing. Okay. In the second picture, biasing is applied. So biasing is applied through current source. So if you take the second picture, for example, this current is PMOS current is mod ID1 because the PMOS current is negative. The current in the PMOS device is negative. Current in the NMOS device is positive. That's why I put the mod. So and this current is ID2, of course. Since the two branches currents are flowing like this, I can write I1 is equal to sum of the two currents. Sum of the two currents. ID1 is the M1 device current. ID2 is the M2 device current. So, and these two currents direction is like this. So that what to do? డైరెక్ట్ గా అప్లై చేశారు డైరెక్ట్ త్రూ డీన్ ఇంజనీరింగ్ కాలేజ్ డీన్ ఒకసారి చేశారు ఓకే ఒకసారి కనుక్కుంటాను ఓకే క్లాస్లో సో what happened? So I1 is equal to ID1 plus ID2. Any wrong? Okay? Yes. And one more thing is, yeah, small signal operation. If you want to go for the small signal amplifier. So I think the I1 current you may connect above or below, no problem. Biasing current, yeah. We can keep it down or up, no problem. Clear? Here is down, here is up. No issue. Suppose if input voltage, this one, is more positive. Okay, what is the difference between this picture and this picture? Here is the M1 is PMOS, M2 is NMOS. Here, changing like this. Whenever you are changing, I1 should be on the top. So here I1 should be in the bottom. Okay. So if V input becomes more positive here because of NMOS transistor, V in is more positive, then ID1 decreases. If more positive means it may goes to the saturation. Am I correct? So decreases, forcing I2 to increase and hence V out to drop. So where you are currently V out this one, because I2 also increases, then V out is nothing but this potential minus this potential. Okay. Okay, NMOS, PMOS cascode in the picture. So NMOS, PMOS cascode means the output voltage, the voltage gain and the output impedance of the circuit can be obtained as calculated from the basic NMOS cascode. NMOS means the basic circuit. In the basic circuit cascode or circuit, both are NMOS devices. Okay, so NMOS, PMOS is the NMOS, PMOS cascode is in the figure. The structures in the second and third pictures. This is the third picture. This is the second picture. Second and third I am considering here are called the folded cascode states because the small signal current is folded up or down. Here, this current is folding up like this. Here, folding down like this. Okay, so that is the reason. That's why it's called the folded cascode. A point of contrast that the bias. So bias current of M1 in M2 and in NMOS cascode amplifier with PMOS cascode load flows to the M2, that is reused. Yeah, reused means here drop will be calculated. Whereas here those M1 and M2 in the second stage, in the second figure, add up to I1. Okay, add up to I1. So since I1 is equal to here is splitting, and here is the both are I1 is nothing but so ID1 plus ID2. Thus, the total bias current in this case must be higher than that in the NMOS cascode amplifier with PMOS cascode load to achieve a comparable performance. So, in this second picture, whatever the picture you have taken, okay, since the I1 is adding up two currents, okay, so the total bias current in this case, in the previous case, is higher than this case. So when come to the large signal analysis means what? Input voltage variation is different, more signal variations. Vin decreases from VDD to 0. It's a large variation. Okay. Earlier it is a VDD. Now your input voltage is making 0. You are bringing to the 0 voltage. So the large signal variation or large signal analysis. Suppose if input voltage is greater than VDD minus VTH1, okay, M1 is off, M2 carries the current of I1 is equal to V1, V out is equal to carries I1, which is equal to the V out is equal to VDD minus I1 R. VDD minus I1 R2. So see this circuit. What is saying? If V1 is decreased from VD to 0, what happened?
Sir, ఒకసారి previous slide వెళ్ళండి.
చెప్పండి.
Sir, previous slide, sir, small signal operation లో second paragraph ఇక్కడ చూడండి. The bias current of M1 in NMOS cascode amplifier with PMOS cascode load flows through M2. It is reused. Ante reused ante just current flowing through M1 from M1 through M2 ana lekapothe reused ki inkedana meaning unda sir?
ఇదేనా?
Dan paina sir. second paragraph.
Second para.
Yes, sir. Yes, sir. Yes, sir. Yes.
Suppose if you take the second picture and third picture. In the second picture, what is that one? Your input device is PMOS.
Yes, sir.
Input device is PMOS and cascode device is NMOS. Okay. So here in the third picture, so reverse. Input is NMOS and cascode device is PMOS.
Yes.
So both the circuits need the biasing, no doubt at all.
Yes.
Okay. Without biasing, the first picture. Okay, biasing is must. So how can you bias these circuits? Suppose for the second picture, in the second picture, I applied biasing here. For third picture, the biasing is applied here. Here I1 is split into the two types, two currents, ID1 and I2.
ID1 and ID2.
And there is a I1 makes the sum of the two currents.
Yes.
So what I'm saying you here folded, why? Because the current folding may be upward or downward. Here the folding is downward.
Yes.
Here is the folding is upward. Sir. Here is the folding. Okay.
Okay.
And remember the point of contrast that the bias current of M1 in NMOS cascode amplifier with PMOS cascode load, okay, flows through the M2. It is reused under what it meaning is, suppose this is the load. So whatever the current, which will make the constitution of the what? Drop. That is the output we are taking.
Yes.
But in this case, it is not like that. Clear? So next case is okay. Yes, here. What is saying? What is the output voltage? Output voltage is equal to output voltage is equal to. So VDD minus I1 into RD. I1 into RD. I am talking about the basic circuit. RD is the above resistance. Okay. So whenever your input voltage is greater than the VDD minus VDH1, M1 is off and M2 carries the current of I1 because already is biased. Okay. So otherwise in the circuit, suppose one is off, definitely the current is flowing like this because this is already biased. Clear? So this is in the saturation, the current may flow like this. So that output is equal to VDD minus I1 into R2. So another case is if Vn is less than the VDD minus VTH1. What is the reason of VTH1 mod? It is nothing but PMOS device I am talking about. Second picture. M1 turns on entering in saturation, which gives ID2 is equal to. Okay, ID2 is equal to I1 minus. So I1 is stop, which minus the current flowing in the M1 device. What is that? 1/2 mu p Cx because of its M1 is a PMOS device. Cx, of course, it is a saturation current. This is the saturation current of the PMOS device.
Yes.
So I1 is the bias current. Understand? So I22 is the
Yes, sir.
I22 is the here I22 is the this current is because of I'm talking about this PMOS device. This I1 minus what is the current here? Suppose if you know this, if it's in saturation, this current you know I1 minus this current is what ID2 because already you have a formula here. Mod ID1 plus ID2 is what I1. If you want to find ID2, I1 minus ID1. That's the formula. Clear? So as Vin drops, input voltage drops. What happened? If the input voltage decreases, what happened? So definitely your ID2 also decreases. Further falling to 0, which makes ID1 is equal to I1. Okay. So Vin is applying to what? Vin is applied to what? PMOS device. So that if the input voltage is fall, because gate is negative is required. Negative potential of the gate is required for the PMOS. That's why I'm telling you, if Vin drops, ID2 decreases. Okay. So then what happened? Your ID1 and I1 becomes equal because ID2 decreases means what is the final value? 0. From the gain formula, you keep ID2 0. Then I1 is equal to mod ID1. This occurs if Vin is equal to Vin1. So I want to show it. So this is the I1 formula in this case. So now I am going to calculate what is the Vn1. What is the Vn1? Vn1 is the voltage of input where this situation will be happen. VDD minus this one. So I can show you this picture. From this picture I can explain. This is the input voltage versus the current. Okay. Suppose input voltage is below the Vn voltage. Below the Vn voltage. What happened? Because PMOS is on. PMOS is on. Input voltage below the Vn particular voltage. So that you will get the I1. Because PMOS is on saturation. So as long as whenever your input voltage crossing this Vn1, so at that time, see, ID2 is 0. Both are different transistors, that's why. So if you increase the input voltage, your ID2 is going to be increasing and ID1 is because the PMOS gate becomes positive, which makes the transistor less conduction finally into the off position. So this is so when ID2 is makes high and I1 goes to 0 means this is the condition. Whenever your input voltage is more than the VDD minus VTH1 mod. And same, one more thing, curve is here, plot is here. Input voltage versus output voltage. For this case, whenever the input voltage is less than the Vn1, again I am telling you, Vn1 is the voltage, input voltage, where ID2 is 0. ID2 is 0. This is. So, for this case, since ID2 is 0, only one current is flowing, your output is VDD. So, as Vin is increasing beyond these levels, definitely, so both the currents will be here in this region, both the currents are significant. So that drop across the RD becomes more, so that your output voltage, the drop across RD is stopped, increasing. So that your output voltage is decreasing. And exactly at input voltage, this is the VDD minus mod VTH1. What happened? Your PMOS is completely off. So that your output is simply VDD minus RD. So, yeah, what is the difference? This is one more circuit, nothing difference. Only the difference is load. I changed the load. I told you earlier we connect here is a RD, but I am always explaining that RD should be replaced with something. No physical resistor. Okay. So that in place of that already what we discussed earlier, cascode of PMOS transistors. So that I kept as the load. That is the only the difference. The rest of thing is same. Only in place of load, what I said, I use that. What is it on the M1? Cascode of PMOS transistors. See, in order to achieve the higher voltage gain, the load of a full net cascode can be implemented as the cascode. Okay. Yeah, this is of course ending. This topic is over. And lastly, choice of device models. We have some doubts. I think in this module, we started from the CS stage. Let us see source follower, let us see, let us cascode, folded cascode. We studied many things. But my doubt is, sometimes we are considering the simple model for gain calculation, for example, for the gain calculation. Sometimes for the same circuit, we are including the body effect and the channel length modulation factors. So whenever you are considering those factors, definitely the gain equation little bit complex. Okay, what should be considered? Actually, suppose in the picture, in the one problem is given. So straight away is asking about the gain without saying anything. Like consider your channel length modulation factor and body effect, or don't consider, is not given anything. At that time, what should be considered? How can you go? Whether you want to go with the simple model equation or by considering these factors. This type of doubts we can get the end of this topic. Okay, how can you resolve these things? Generally, for what is considering or taking the solution of this type of issues, we need some experience. Definitely. So based on the situation, sometimes it's required. So otherwise, we cannot take. Whether you propose the same problem, you can use the simple formula to calculate the gain, and for the same problems, you can use all the factors, consider all the factors, and solve it. Both may be correct. But when it comes to the industry, so definitely, so the personal experience and institutional considerations are very important. So the voltage gain of generated degenerate common source stage can be simplified as yes, this is already visible. What is the voltage gain of the CS with common CS with the source degeneration? RD by minus RD by 1 by GM plus RS. This is the formula. Simple formula without considering the yes. Suppose when you consider those factors, this formula becomes like this. So how does one choose a sufficiently accurate device model or expression? Which one should be considered? Okay. So for that, some small instructions are there. So first, break the circuit into number of familiar topologies. Suppose it's a big one. Concentrate on each subcircuit and use the simplest transistor model. First of all, the simple voltage dependent current source, perfect, operating in saturation for all the transistors. And next, if the drain of the device is connected to the high impedance drain, okay, or example, or drain of another, two drains are joined together. So then add the R naught. R naught is the what? Output impedance of the device. Internal, of course. Okay. Otherwise, we can remove the R naught. When we need to add the R naught, consider the R naught, then we need to neglect the R naught. So, if the drain of a device is connected to the high impedance, then consider the R naught. So, at this point, the basic property of most circuits can be determined by inspection. And one more thing is more accurate iterations. Iterations means number of trials. The body effect of the device whose source or bulb is not at a AC ground can be included as well. Okay, body bias will be considered whenever what is saying. So whose source or bulb is not at AC ground. Because body effect means what? Generally in the mass devices, our source and the body or bulb joined together and connected to the ground. Okay, if not practically, if the body, if the bulb potential is somehow less than the source, then body effect will come into the picture. So let's look at the terminals properly. So for bias calculations, it is usually adequate to neglect the channel modulation body effect in the first pass. But in the second time, after one time it's over, then go with the constellation. So if you begin with them, then little bit confusion may come. Okay, these are the things we need to understand. Okay, because in the second module, the number of circuits, more number of circuits, more number of equations, same common source amplifier, common source stays with the different types of loads we have considered. Okay, we have a different each individual circuit will have a individual different advantages and disadvantages. And moreover, we have it. So for each circuit, we have a simplified models and body bias and body effect and the channel modulation factors, additional factors. So we will get the confusion when we get the one problem how to solve it. If the problem is not clear, is not clearly mentioned about whether you want to take all these or not. Okay, clear. So at that time, choose your own path. Choose your expectation means what? Whether do you know simple formulas, complex formulas, and whether whatever the data you have, main data is to be required. Suppose if you want to include to calculate the voltage can include it with the body effect and channel modulation, definitely you need alpha, gamma, and yes. So these factors you need. Clear. So read the question. If the data is available, then you can go with this. If data is not available, how can you take this data? Okay. Okay, I will stop here. If you have, I think second module is over.